Next, we're going to continue our discussion of probability distribution functions. And again, what these PDFs do is help characterize how items are distributed in a population in terms of, for example, what proportion of people have a GPA between 3.5 and 4.0. Now, starting in this subsection, we're going to talk about particular probability distribution functions that have names attached to them. As you might expect, since they have names attached to them, they have a lot of good applications. And so our first particular PDF that we're going to look at is one that's called a discrete uniform probability distribution function. Given the name discrete, it's for a discrete random variable. And the uniform comes into play because basically every particular item in the population, or every possible occurrence in the population, has an equal probability assigned to it. So let's define that more formally. Let's let y be our discrete random variable. Then let's say that y can assume particular values, which we just simply call y1, y2 up to yk. So it has k possible different values. And the probability that y is equal to y1, or the probability that y is equal to y2, and so on, is equal to 1 over k. That's again where the uniform name comes in. Every possible item that a y can take on has an equal probability. So this is a very, very, very basic distribution, and it gives us a place to start with when we're talking about these named distributions. Now, as we've seen before with the probability distribution function, we can find the expected value of our random variable. We can find the variance of a random variable. And so, using our expressions before that we've seen for in general probability distribution functions, the expected value of y, in other words, mu, is equal to the sum of our possible values of y. Again, y, sorry if I didn't mention this before, will be like a numerical value. We'll look at an example of its application shortly. Expected value of y is equal to the sum of all the possible values of y divided by k. The variance of y, also known as sigma squared, is the sum of all your y, subtract off mu squared, divided by k. Well, let's look at this more closely. Why do we have these expressions? So in general, the expected value of y is the sum over all the possible values that y can take on. And what we're summing is y. And we're multiplying it by a weight, that corresponding probability. So in this particular case, we can have y1, y2 down to yk. Again, these will be like numerical values, like maybe 1, 2, 10, 100, and so on. That's what these y's represent. And so if we just simply sum up all the y's and weight all of them by 1 over k, that's how we get our expected value of y. And in a similar manner, we can find the variance of y as well, going back to our original definition of what the variance of y represents. Okay. Now, like I said, this is a very basic probability distribution function. It gives us a place to start when we're talking about these named probability distribution functions. And so a very basic example where it can be used is with respect to rolling a die. So let's let y be equal to the result from throwing a die, or rolling a die. Now, this is going to be a six-sided die, so the possible values that y can take on are y1 is 1, y2 is 2, and so on, up into yk. In this case, k is going to be 6. Y sub 6 is equal to 6. Each has equal probability of 1 over 6 of being actually rolled. Any other possible value of y, of course, will be 0, because there's only those 6 different values on a regular six-sided die. Notice if I were to sum up over all the possible values of y here, let's actually change that a little bit there. I would get 1. I sum up all the probabilities. I have to get one of those possibilities. Then if we were to find the mean, again, we would sum up all the values of y, divide by the total number of possible outcomes, which is 6, and we get 3.5. Do a similar thing with the variance, then we get 2.9. So notice here again how the mean, or what you would expect on average to roll, doesn't have to actually be a potential thing that you can actually roll. Obviously, you can't roll a 3.5. Well, how can we do some of these calculations in R? Well, real simply, we create a vector y that has the values of 1 through 6 in it. We create an object called fy that represents f of y, which is 1, 6. Define the mean. I take all my y's times the corresponding 1, 6, and I sum them all up. That's how I get my mu. Do a similar thing again for the variance. I don't know why that 2 is there. Then in Sage, we can go ahead and do a similar process. Again, we use the sum function to do the necessary summing that we need. So with that, that's just a very brief introduction to a discrete uniform probability distribution.